Hello everyone, myself Aparna George, Assistant Professor of Applied Electronics and Instrumentation Department, Rajagiri School of Engineering and Technology, Kochi. I welcome all to the lecture from the subject Logic Circuit Design. The topic is Binary Codes. The contents under this topic are BCD code, XS3 code, break code, ASCII code, error detection and correction codes. What are binary codes? It's a coding system which will use the binary digits 0 and 1 to represent a digit, letter or other character in a computer. They are classified as numeric codes, alphanumeric codes, error detection and correction codes. So first one, numeric codes. They are codes which represent only numeric information, that is only numbers as a series of zeros and ones. Numeric codes used to represent the decimal digits are called binary coded decimal or BCD codes. These BCD codes may be weighted or non-weighted. What are weighted codes? Weighted codes are one which will obey the position weighting principle. Position weighting principle means each digit position of the number represents a specific weight. So for example, one of the weighted code is BCD code. So decimal number 9 is represented as 1001 in BCD code. So the weights of 1001 are 8, 4, 2 and 1 respectively. So these weights can be also represented as powers of 2, that is 2 power 0, 2 power 1, 2 power 2, 2 power 3, which are nothing but 1, 2, 4 and 8. So other examples of weighted codes are 2421, 5211, 3321. So next, non-weighted codes, they are the one which will not obey the position weighting principle, that is no weight is assigned to the digit positions. Example are XS3 and break code. So one of the most commonly used weighted code is 8421 code. It is also known as BCD code. BCD means that each decimal digit 0 through 9 is represented by a binary code of 4 bits. The designation 8421 indicates the weights of the 4 bits. So they are represented as powers of 2, which I have mentioned earlier. So usually with 4 bits 16 numbers can be represented, but in 8421 code only 10 of these are used. Rest of the 6 code combinations 1010, 1011, 1100, 1101, 1110 and 1111 are invalid here. So we will see an example in which a decimal number is converted to binary code. So a decimal number 24 is given. So it's having 2 digits 2 and 4. So first we will take the digit 2. So its corresponding weights are written here, that's 1, 2, 4, 8. So we require the place value of this position. So we will write 1 here. So rest of the place values are not required. So we are putting zeros there. So our code is 0010 for the digit 2. So similarly for 4, the positional weights are written 1, 2, 4, 8. We require the place value of this position. So there 1 is written, rest of the place values are not required. So we are putting 0. So the corresponding BCD code of decimal digit 4 is obtained. So other weighted codes are 2421, 5211, 5421. So we will just take 5211 code. So its weights are 5211. That means the weight of each positions. So we will just take a decimal digit 7 and how it is written in 5211 code. So decimal digit 7. So in order to get 7, we know that we require the place value of 5 and 2, as 5 plus 2 is 7. So rest we can write 0. So the resultant code is 1100. Next is XS3 code. So it's a non-weighted code. XS3 code of a binary number is determined by, first we have to find the decimal number of the given binary number. Then we have to add 3 in each digit of the decimal number. Then we find the binary code of each digit of the newly generated decimal number. We have to simply add 3. So we will see an example. So a decimal number 237.75 is given. So what we have to do is simply add 3 with each digit. So 5 plus 3, we will get 8. So its corresponding code is written. 7 plus 3, it's nothing but 10. Its corresponding code is written. Again 7 plus 3, 10. Its corresponding code is, binary code is written. 3 plus 3, it's 6. Its corresponding code is written. 2 plus 3, it's 5. Its corresponding code is written. So we can also add 0011, that is 3, in each 4-bit BCD code of the decimal number for getting XS3 code. So it's shown in this table. So decimal digits you can see here, its corresponding BCD code is written. So in order to get XS3, you have to simply add 0011 with each BCD codes. For example, if you are taking 3, decimal digit 3, its corresponding BCD code is 0011. So if you are adding 0011 with this BCD code, we will get 0110. Next is gray code. This is another unweighted code, that is, there is no specific weights assigned in the bit positions. Again you can see the gray code table. Decimal digit 0 to 9 is written. Its corresponding, you can see the corresponding gray code. So if you are taking the gray code of decimal number 0 and the gray code of decimal number 1, you can see that there is only a single bit change. Rest of the bits are same. Again, if I am taking the gray code of decimal digit 4 and decimal digit 5, you can again see that there is only one bit change, others are same. So you can say that here each number differs from previous number by a single bit. Next we will see how a binary number is converted to gray code. So the steps are: the most significant bit in the gray code is the same as the corresponding most significant bit in the binary number. Going from left to right, add each adjacent pair of binary code bits to get the next gray code bit. Discard if there is any carry. So we will see an example. A binary number 11101 is given. So its bits are clearly shown. That's bit 1, bit 2, bit 3, binary bit 4, binary bit 5. So correspondingly the gray code bits, gray code bit 1, 2, 3, 4 and 5 is written. We will see how the gray code is obtained. So the first step is the MSB of the gray code is same as that of the binary number. So it's written as such. So next what we have to do is we have to add each adjacent pairs. So 1 plus 1, you will get 0 with carry 1, that carry 1 is omitted. Again 1 plus 1, you will get 0 with carry 1 is omitted. Next 1 plus 0, it is 1. Again 0 plus 1, it is 1. This is how the gray code is obtained. So our resultant answer is 10011. So we will see another example. A binary number 10110 is given. We will see how it is converted to gray code. So MSB is the same. So MSB is written as such. So next adding adjacent pairs, that is 1 plus 0, you will get 1. 0 plus 1, you will get 1. 1 plus 1, you will get 0 with carry 1 is omitted. Again 1 plus 0, you will get 1. Okay. So next is how a gray code is converted to binary code. So the steps are: the most significant bit in the binary code is the same as the corresponding bit in the gray code. Add each binary code bit generated to the gray code bit in the next adjacent position. Discard if there is any carry. So we will see the example. A gray code is given, that is 1010. So its bits are clearly shown. So the first step is the MSB is going to be the same. So it's written as such. So next what we are going to do is the binary bit that is generated, it will be added with adjacent gray code bit. So 1 plus 0, you will get 1. Again 1 plus 1, you will get 0 with carry 1 is omitted. Again 0 plus 0, you will get 0. So the final result is 1100. So we will see one more example. A gray code 11011 is given. So how to convert that to binary code? So MSB is written as such. So the generated one, it will be added with, that is 1 plus 1, you will get 0 with carry 1 omitted. Then again 0 plus 0, that is 0. 0 plus 1, it's 1. Again 1 plus 1, it is 0 with carry 1 is omitted. Okay. So numeric codes are over. Second one is alphanumeric codes. These are the codes that represent numbers and alphabet characters. These also represent symbols, spaces, question marks, colons, semicolons, etc. The common alphanumeric code is ASCII. So ASCII stands for American Standard Code for Information Interchange. This is universally accepted alphanumeric code which are used in most of the computers and most computer keyboards are standardized with ASCII. So when you press a letter, number or control command, usually the corresponding ASCII code goes to the computer. So this has 128 characters and symbols, and they can be represented by 7-bit binary code. So totally 128 characters and symbols. So the first 32 ASCII characters, they are non-graphic commands which are never printed or displayed, and they are only used for control purposes. Rest are the graphic symbols. For examples, capital letters ABC, small letter ABC, numerals 0 to 9, dollar symbol, at the rate, less than symbol, greater than symbol, etc. So here you can see the 128 characters and symbols used in ASCII code. So the first 32 are the control characters, that is from decimal 0 to 31, and the rest of them are graphic symbols, that is which are represented in decimal as from 32 to 127. So here you can see the decimal, binary and hexadecimal equivalent of each characters and symbols. So binary, it is represented by a 7-bit code. Next, extended ASCII characters. So apart from the 128 characters we discussed, there are additional 128 characters that were adopted by IBM for use in their PCs. So it is represented by an 8-bit code series from hexadecimal 80 to FF. So the additional 128 characters include foreign alphabetic characters, Greek letters, mathematical symbols, shading characters. So this is the extended ASCII characters, which are from 128 to 255 in decimal representation. So totally there are 128 plus 128, that is 256 characters and symbols in ASCII code. So third one is error detection and correction codes. So when digital signals are transmitted from one circuit to another circuit, error may occur during transmission. So change of a 1 to 0 or a 0 to 1 during transmission is known as error. This should be detected and corrected for transmission and storage of digital data. So one of the commonly used error detection method is parity method. So many systems use parity bit as a means for bit error detection. So if you take any group of bits, it will contain either an even or odd number of ones, and this can be easily checked. So based on this information, an additional bit can be added with the original data. So if we take 8-bit data, adding the parity bit will make it 9-bit long. So at the receiver side, what happens is the parity is again calculated and matched with the received parity. So if they match, data will be okay, otherwise data is correct. So there are two types of parity bit, that's even parity and odd parity. So even parity checks if there is an even number of ones. If so, parity bit will be 0. Otherwise, the parity will be 1. Odd parity, it will check if there is an odd number of ones. If so, parity bit is 0. Otherwise, the parity bit will be 1. Again, parity bit will only provide for detection of a single bit error. It cannot check for 2 errors in one group. So if we are transmitting a BCD codes 0101 and we are including an even parity bit, then the parity bit which should be transmitted should be 0. As it's even parity, if you are looking here, you can see that the number of ones is 2, that is even. So the parity bit should be 0 in order to make this group even. So next is error correction code. So the error correction code discussed is Hamming code, error correction code. So this code not only detects bit error but also identifies the bit that is in error so that it can be corrected. So this coding method uses a number of parity bits which can be located at different positions in the code group to enable error detection and correction. This is only used for single error detection. So these error correcting codes are usually used in memories, networking, hard disk, CD-ROM, DVD when we store bulk of data in memories and all. So I told that number of parity bits will be located at different positions. So first step, we have to find how many number of parity bits should be used. So let m be the number of information bits that is to be transmitted and let p be the number of parity bits. Here it has to satisfy a relationship that is 2 power p is greater than or equal to m plus p plus 1. For example, if we are taking the number of information bits, that is m, as 4, just take p, that is number of parity bits, as 2. So if you are substituting this m and p in this equation, we will get 4 is greater than or equal to 7, which is not satisfied. So what we have to do is, we have to take the number of parity bits as 3 and substitute that in that equation. So we will get 8 greater than or equal to 8, which means the relationship, the particular equation is satisfied. So here, adding the number of information bits 4 and number of parity bits 3, you will get 7 bits. So along with the information bits, 3 parity bits are added. So here 3 parity bits are required to provide single error correction for 4 information bits. So number of parity bits is found. So the next step is where to place this parity bits in your code which is to be transmitted. So same thing, number of information bits 4, number of parity bits 3, so totally 7 bits. So bit 1, bit 2, bit 3, bit 4, bit 5, bit 6, bit 7. So usually the parity bits are located in the positions that are numbered in ascending powers of 2. Numbered in ascending powers of 2, that is 1, 2 power 0, 1, 2 power 1 is 2, 2 power 2 is 4, 2 power 3 is 8, 2 power 4 is 16, and so on. So here the 7 bits, so P1 should take the first position, P2 should take the second position, next parity bit should come in the fourth position, that is of P3. So third bit will be the first information bit M1, fifth, sixth and seventh position will be M2, M3, M4. So the parity bits are placed. Next is assigning values for the parity bits. So how to assign values for the parity bits? So for that we have to create a bit position table. So bit position table, it includes bit designation, that is P1, P2, M1, P3, M2, M3, M4. Under that we have to write the bit position, that is first, second, third, fourth, fifth, sixth, seventh. So corresponding binary position numbers are written. So that is binary value of this bit position is 001, this is 010, this is 011, this is 100, this is 101, this is 110, and this is 111. We have to use 3 bits. So this is a bit position table. We have to write the information bits and parity bits. Again, this parity bit will check all the bit positions including itself that have ones in the same location in the binary position numbers. So we will take the parity bit P1. So if you are looking here, you can see that the binary position number is 001. So the rightmost bit is 1. So we will see which all positions have rightmost bit 1. So this position, and this one. So parity bit P1 will check bit positions 1, 3, 5 and 7. So next, parity bit P2. If you are looking here, the binary position number of P2 is 010, that is the middle bit is 1. So we have to check the bit positions having the middle bit 1. So that is 3, 6 and 7. So the parity bit P2 will check the bit positions 2, 3, 6 and 7. So next, take P3. So P3, the binary position number is 100. So here you can see that the leftmost bit is 1. So we have to check the bit positions with the leftmost bit 1. This one, this one, this one. So the parity bit P3 will check the bit positions 4, 5, 6, 7. So this will become clear when we see an example. So you have to determine our question is determine the single error correcting code for the BCD number 1001 using even parity. So our information bit is 1001. If you are looking here, you can see that there are 4 bits. So our M is 4. So if you are substituting M as 4 and P as 3, the particular equation will be satisfied, and the total code bits you will get is 4 plus 3, that 7 bits. So parity bits is found, that is 3. So next we have to construct bit position table and have to enter the information bits, that is 1001. So we require 7 positions. Their binary position number are represented by 3 bits. So here the information bits are written here, that is 10001. So we have to find and assign value for parity bits P1, P2, P3. So parity bit P1, so it will check the positions 1, 3, 5 and 7. So if you are looking here, you can see that it will have a code group of 1, 0 and 1. So if you are looking here, you can say that the number of ones are even and satisfying the even parity. So your P1 should be 0 in order to make this code group even. Next we will take parity bit P2. It will check bit position 2, 3, 6 and 7. So here the code group is 1, 0, 1. Again the number of ones in this group is 2, that's even. So P2 should be 0 in order to make it even. Next P3. P3 will check the positions 4, 5, 6 and 7. So you will have a code group of 0, 0, 1. Here you can see that the number of ones is odd. So in order to make this code group even, P3 should be 1. So parity bits P1 is 0, P2 is 0 and P3 is 1. 0, 0, 1. So this is how the parity bits value are assigned. So next is how to detect and correct an error. That means in which position, in which bit position there is an error and we have to correct that. So the step 1 is start with the group checked by P1. Step 2, check the group for proper parity. A 0 represents a good parity check, a 1 represents a bad check. Step 3, repeat step 2 for each parity group, and step 4, formation of error position code. So it will be clear with an example. Assume that a code word 0011001 is transmitted and that 0010001 is received. So designate any error that has occurred in transmission if even parity is used. So your transmitted word is 0011001. So you have received as 0010001. So you can clearly see that at the fourth position there is an error. So we have to find out this. This transmitted one will include the information bits and parity bits. So first we will make the bit position table with bit designation, bit position, binary position number. So I have written the received code is here 0010001. So we have to check the parity bits. So P1 will check 1, 3, 5 and 7. So here we will have 0, 1, 0, 1. So if you are looking here, this code group contains even number of ones. Even number of ones, so the parity check is good. Next we will check the parity bit 2. So it will check bit position 2, 3, 6 and 7. So if you are looking here, this code group contains 2 ones, that is even. So again the parity check is good. Next we have to check the parity bit P3. So P3 will check bit positions 4, 5, 6, 7. So if you are looking here, this code group has only 1, so that is odd number of ones. So here the parity bit check is bad. So if the parity check is good, we will put 0, and if the parity bit check is bad, we will put 1. So finally we will get a code that is 100. So this is MSB and this is LSB, that is the least significant bit and most significant bit. So we got a code 100. So this code 100 is the error position code. So 100 is nothing but it's a binary of decimal digit 4. So you can say that the bit in position 4 is in error. It is a 0 and should be 1. So in the question, the received code was 001 0 0 0 1. So here the bit in 4th position is in error. It is 0, but actually it should be 1. So corrected code will be 0 0 1 1 0 0 1, which agrees with the transmitted code 0 0 1 1 0 0 1, that is 0 0 1 1 0 0 1. So this is how error is detected and corrected. Okay, the lecture is completed and thank you everyone.